I wanted to show you the effect of all the different alternatives in terms of modeling for the bin packing problem. And what I propose now to measure is the number of failures that we detect for this problem. So we have here a small instance, that's the items that I need to place, and that represents the height of each of the items. We have the decision variables, so that's the decision variables, that's the decision for which bin I will decide for each of the item. That's the load variable of each of the bins. Okay, you see that it's up to the capacity plus 1. And then we have the modeling of the bin packing. That's the Boolean variable that tells me for every bin if this item is placed in that bin or not. We multiply by the corresponding weight. Okay, these 0, 1 variables, we multiply it by the weight, and then we do for every bin the sum of the weights. That's either 0 for each item, or that's the corresponding weight of the item. Okay. So for the search, I will simply here have a search that will enumerate all the possible bins for each of the items. Okay, and I will decide the bin increasingly in the increasing direction. And for the variable, I simply take the next item that is not yet decided. So if I do that and I run my model, the output that I see is, of course, I will print here the solution. I will print X. And so that's the bin for each of the items that I have in my problem, and that's the load variables. Okay, if I do this model like this, very naive model, I've got more or less 1,000 backtracks. The first thing that I can add is this redundant constraint that will sum the load variables. Okay, I will sum the load variables and we say that it's equal to the sum of the weight of all the items. So if I add this redundant constraint, I will probably be able to reduce a little bit the number of failures. You see that I only have 315 failures simply by adding this property that I will express as a redundant constraint, and it will improve the communication between all these sum constraints. Okay, the next thing that I can do is break the value symmetries, because as you know, we have a value symmetry. We can always flip two different bins. And for instance, you see that the bin 0 and 1, we could flip them. And to avoid that, we can flip them and explore this symmetrical space. I can impose an ordering to say that the load of the bin variable should be increasing. Okay, and I can use less or equal constraint for that. And I will impose that the load of the variable should be increasing. The problem is there that the first solution that I'm discovering is violating that constraint. You see that the first bin has a load of 9, while the second bin has a load of 8. So if I impose an increasing weight there in terms of load of the bin, they need to be flipped. And so this solution will disappear. And so I'm expecting that we'll have a bagged effect by adding this breaking of the symmetry constraint, because this first solution will be removed, will not be a feasible solution anymore if I pause this constraint. Let's see what it gives. So I have 315 backtracks. If I impose that constraint, what happens now is that you see that it has increased 1,386 backtracks. So that's worse. Okay, so that's exactly the bad effect of breaking the symmetries with constraint. It's possible, if you are lucky, that you will remove the first solution that you were able to discover before. Okay, and so it's not always clear that you will strictly decrease the number of backtracks. So let's try the alternative way of breaking the symmetries, which is doing it dynamically during the search. And if I want to break the symmetries dynamically during the search, I can, for instance, avoid to explore alternatives that correspond to placing an item in two different empty bins. So I will simply get there the maximum bin that is in use in this partial solution at that point. And I will, instead of trying every possible bin, I will try at most one empty bin. So you see that my for loop there is stopping at maximum to this maximum used bin plus 1. And the plus 1 is to say I want to explore just one more empty bin, but not more than one. Okay, let's see what it gives in terms of number of backtracks. And you see that the number of failure is only 61 in that case, so that's very little. And as you see, my first solution is still the same. It didn't change. I'm still able to discover my first feasible solution, and so we have all the benefits there. So the best model there is adding the redundant constraint and also breaking the symmetry dynamically during the search to avoid exploring symmetrical search in terms of empty bins.